Hi guys, we're going to start with fundamental terms in chapter 1. To get started, let's draw a picture here. So let's draw something that looks like that. Okay, so you might be wondering, what is that supposed to be? This is going to be a piston cylinder assembly. Alright, so that outside frame is going to be our cylinder, and then in here is our piston. Now this piston can go up or down, and underneath the piston is going to be some sort of substance. So for now, let's just say it's carbon dioxide, so we got CO2. Now as this piston moves up and down, think about what happens to this space right here. Right? If the piston moves up, this space is going to increase. This space is a volume, right? Because this is think of a 3D cylinder. You've got a volume here, so volume would increase. And then the pressure felt in here, that would decrease, right? Because the CO2 has more room to expand. So we would reduce our pressure. Now if we move the piston down, we would reduce the volume, and then pressures are going to go up. All right, so these are the types of problems we're going to start out with. Now looking at what this is, this whole little drawing we did, this is what we want to study. Now the word we're going to use for that is system. So when I say look at the system, I'm just talking about look at whatever it is we're wanting to study. Now everything external to the system, so out here for example, those would be the surroundings. Okay, so surroundings are external to the system, and what determines the cutoff point between the system and the surroundings is the boundary. Right. Now we're going to have two kinds of systems. This kind of system we have here, if you look at it, there's no way for the CO2 to escape. Right? It can't leave the cylinder because the piston's keeping it in. This is going to be a closed system. A closed system is one that always has the same matter. So that means there is no mass transfer across the boundary. So there's no mass entering your system, there's no mass leaving your system. It's always going to stay the same. So that's a closed system. We are going to start out by analyzing this kind of system because these are simpler to analyze. Now if we have a closed system that doesn't interact with the surroundings, we are going to say that that is an isolated system. Okay. Now next, eventually we're going to talk about systems where we have mass flowing in and out. So this is kind of the opposite of a closed system. In that case, we're going to say we have a control volume. Okay, so a control volume is going to be a space through which mass can flow. All right, so in that case, mass will cross the boundary of your system. So you'll have mass going in and out of your system. Now when we have a control volume where we've got this mass flowing, we need to pick our boundary so that we have convenience. We want it to be convenient for us when we're doing our analysis. So there are a couple things we need to think of. The first one, or the main one, is going to be where is the mass entering and leaving the system. So that's going to be an important question to answer. And the reason for that is typically it's easiest to make the boundary lines be perpendicular to your mass that's flowing in or out. And you'll see that when we get further on in the chapter when we start dealing with control volumes. But this is going to be our main thing we want to look at. So where is the mass entering and leaving? And then the other question is, what is the goal of the analysis? So what are we even looking for? Okay. And we'll talk about this more later as we get to problems with mass flow. All right, so next, flip to the next page here. Next, let's describe the systems and their behavior. Okay. Now, the first approach we're going to have is the macroscopic approach. So that's what it's called. And for this kind of approach, we're just looking at overall behavior. Let's try to focus that in a little bit. All right, we want overall behavior. So we're going to look at things like pressure, temperature, things like that. Things that you can get a measurement. So if we have a pressure gauge, we could find pressure. That is looking at things through the macroscopic approach. This is also called classical thermodynamics. And this is the approach that we are going to use in this course. Now there's a much more detailed approach. That's the microscopic approach. And this approach is also called statistical thermodynamics. So this is going to be where you look in a lot more detail. You don't just look at the overall behavior. And this approach is going to be used in very specific applications. So when you're dealing with lasers or high-speed flows, things like that. So we aren't going to do this approach. We will do macroscopic approach because we want to look at the overall behavior. So next, let's talk about property, state, and process. So when we talk about a property, we are talking about a macroscopic characteristic like mass, volume, temperature, for example. Those are all properties. And with those properties, we can assign a numerical value at a specified time. Okay? And to assign that value, we do not need to know the past history. So if I want to know the mass at 10 seconds in an experiment, I don't need to know the mass at 2 seconds, right? Because they're not really related to each other. We don't need the past history. Right, so that is a property. All right, now next we're going to have the state. So when we talk about the state, we're just talking about the system as it is described by its properties. So if I go ahead and draw another piston cylinder assembly like this, and in here there's some gas. Now at the initial time, let's just say t equals 1, I can find the pressure, the volume, and the temperature in this area right here. Okay. Now this would be a state. So normally we would say this is state 1. Okay, because this is our initial state. Now if the piston were to move, so let's say we go to t equals 5, and at t equals 5 the piston has moved to the right, for example, we're going to have a new pressure, a new volume, and then we can find our temperature. So now this would be state 2. Okay? So the state is just the conditions you have at a given point in time. Right? And you can find all of your properties at that time. That gives you your state. Now here I went from state 1 to state 2. Okay, my pressure is going to change, volume is going to change, etc. So I'm going from here to here. This is going to be called a process. Right? So a process is when any of the properties change in your system, and then that's going to make the system's state change. So we say the system has undergone a process. Okay? So all that means is you're going from one state to another state. This next term is going to be important because we will use it. This is going to be one of our keywords that we're going to highlight when we get to our problems. This term is steady state. So steady state, what that's going to mean is it's going to mean that none of your properties in your system change with time. So time here is the important thing. All right, so if you think about a function, if you were to write out a function, if I had a pressure function, there would be no t in the equation. Okay, because it's not going to change with time. So that means if I were to look at an equation like this, where E is energy, this would be the time rate of change of energy. If energy is not changing with time, this derivative goes to 0. Okay, so this steady state term is going to be important later on because it's going to allow us to make simplifications like this. Okay, so we'll get to this when we get to our examples. But that's what steady state means. Just properties are not changing with time. Okay. Now let's do a couple other things. Let's go over extensive and intensive properties. Move this page up here. So these are going to be our classes of properties. So the first one let's talk about is extensive. Okay. So for an extensive property, just to demonstrate this, let's draw this little picture. So let's say this is a block, some substance, and it's got a mass of 3. Okay. Now I could go, if I wanted, and I could cut this block into 3 equal parts. All right. And then to get the total mass of these 3, I would just sum up the masses of the individual parts and I'd get 3 again. Okay, so here, when we say an extensive property, basically we have a property where your value for your overall system is going to be the sum of the value of its parts. Okay? So if you could cut it up into parts like this and then add up each individual part, get your overall value, you have an extensive property. Okay? So mass, volume, and energy are examples of extensive properties. And these can change with time, but not position. Okay? Now, the opposite of that is going to be an intensive property. So an intensive property can vary from point to point, but it's not going to be additive. All right? So examples of that would be pressure, temperature, and something called specific volume, which we'll go over in just a little bit. So if you think about a room with temperature, you can't divide up your room and then take the sum of the temperatures for the different pieces of the room, right? It doesn't make any sense because the temperature is going to be constant throughout, typically. So that's an example of an intensive property. If you can't cut it up into pieces and do the sum, it's intensive. And let's cover equilibrium and then we'll stop on this video. So for equilibrium, when we're talking about thermodynamics, we've got several different types of equilibrium that have to be reached. All right, so we got mechanical, thermal, phase, and then chemical equilibrium. So in thermodynamics, this is going to be a little more difficult or a little more involved than what you might have seen in, say, a physics class or a statics class, where you're just looking at a system and then finding your one equation, the sum of forces equals 0 equation. That's what you had to do. Here, you got more to think about than just that. Okay? Now let's go back, talking about equilibrium. Remember we said if a system is isolated, it doesn't interact with the surroundings. Even though it doesn't interact with the surroundings, the state can still change because of internal events. Okay? And let's think about temperature and pressure tending towards uniform values. Right? So these would just be internal events making our temperature and pressure try to go to a uniform constant value. So at equilibrium, all of those changes are going to stop. So the temperature and pressure have reached uniform values, so all of the internal events stop happening. Then we say we're in equilibrium. Okay? So we're going to assume temperature is uniform throughout our system and that pressure is going to be uniform also. Right? As long as gravity effects are negligible. Alright guys, so that's the end of that section. I know that was a lot of terms and definitions. Eventually we'll get to some examples. So I will see you guys in the next video.